In this video, I will go over the homework that follows the second part of the lecture on comparison tests, in which we learned the limit comparison test. And as always, I hope that you watched the lecture first. And let's go ahead and jump right into the homework. And the first question is to analyze the convergence of this, actually not this, this is what we're going to compare it with, but we're analyzing the convergence of this series. And the limit comparison test says that this series behaves exactly the same way as this series under certain conditions. I'll discuss those conditions in a bit. But what do we know about this series? We know that this series is actually P series, and with P equals to 1/2, which is less than or equal to 1, therefore it diverges. So under certain conditions, we'll be able to conclude that this series diverges by the limit comparison test. But what are the conditions? So when are we allowed to make such a claim? Well, we're allowed to make such a claim when the limit as n approaches to infinity of the general term of the original series divided by the general term of the series with which you compare it against is equal to some value L, which is not 0 or infinity. And, well, this process involves finding this limit. And I'm just going to simplify these expressions. And we can see that for multiple reasons, one of which is if I divide everything by the square root of n, I'm going to end up with this. And this goes to 0, so the whole thing is approaching to 7/5, which is less than infinity and greater than 0, and this will allow us to conclude that these two series behave the same way. And since one of them is a diverging P series, that implies that the original series also diverges. So this type of reasoning is called the limit comparison test. Let's go to the next problem. And in this problem, even though it's not asking us this way, but it's a setup for determining the convergence of this series. And we are comparing it with this series, which is a P series with P equals 2, which is greater than 1, therefore it converges. So as soon as we establish this fact, we would conclude that this original series converges by the limit comparison test. Now, how do we establish this? We establish this by finding the limit of the general term of the original series divided by the general term of the series against which we're making the comparison. And now this limit, it's a lot of writing, but this limit can be found like this. So we have, so 6n squared goes in the denominator, and n squared can be distributed. So we have 3n to the 6 minus 16n to the 4 plus 16n squared, and we divide all that by 6n to the 6 minus 32n to the 4 plus 32n squared, and the polynomials at infinities behave just like their leading terms, so this whole limit will be equal to the limit of 6 times 3n to the 6 divided by 6 times n to the power 6. As n goes to infinity, everything cancels. The answer is 3. 3 is less than infinity, n is greater than 0, and therefore we established this equivalence in terms of behavior between the two series. Of course, I cannot put the equal sign there because the limits are not the same, but that's why we had to be creative and invent a new symbol to demonstrate that their behavior is similar. All right, so the answer is 3. So we're given the following series. We're comparing it against this series. This series is geometric. The common ratio is 9/2, which is greater than 1. So this series diverges. Therefore, this series diverges by the limit comparison test as soon as we prove this equivalence. And to prove this equivalence, we have to set up the limit as n goes to infinity. In the numerator, it's the general term of the original series. In the denominator, it's the general term of the series against which we make a comparison. We continue finding this limit, and simplifying. And we have 1 plus 9 to the power 1 minus n. This term goes to 0, so the whole limit is equal to 1, which is a number between 0 and infinity. So we established the equivalence, therefore those two series behave similarly, therefore the original series diverges. That's the reasoning. And we have another similar one. And we're comparing it against this one. And this one is a geometric with the common ratio 4/3, which is greater than 1. Therefore, this series diverges. So as soon as we establish the equivalence, we would conclude that this series diverges as well. Now, to establish this equivalence, we have to set up this limit as n goes to infinity of the ratio of the general term of the original series over the general term of the series against which we make the comparison, and this limit as n goes to infinity is equal to this. Simplify. And this term goes to 0, this equals to 1, which is a number between 0 and infinity. And therefore we established this equivalence, and therefore the original series diverges because it behaves the same way as another geometric series with a common ratio greater than 1. So that's the reasoning. And this would be the last problem. And if you have any questions, please feel free to reach out.